I'll disconnect this call. Sorry for that. Yeah.
Yeah.
Sorry. Okay. So now, what we were saying is like,
Metasurface and metamaterials. Yeah.
meta materials, right? So meta surface, no, we were telling that, for example, see, there is a, mm, oh, okay, I have to request for control.
Okay.
Yeah.
Approved.
Okay. Okay. So now, see, the thing is, we might have studied, as a law of diffraction and all, right? Usually we'll go like this, right? In a conventional medium. This is, let's see, it's a free space. Then you are entering into the medium, or sorry, this medium, and then you will see the, diffraction is like this, right? But in metamaterials, we will see that diffraction go in this fashion, right? Because of this, so as I mentioned, right? For example, if you create a split ring resonators, it will trap the signal. So you will get an illusion that the signals are going in reverse direction, correct? So the signal is flowing, but the thing is, it is getting trapped somewhere. That's why you will feel that it is kind of the signal is flowing in the reverse direction. You will get a feel, right? That is due to this negative permittivity or permeability, like that, whatever you are achieving, right? So in
Mm.
this, no, you are using 2D, three-dimensional one. That the two-dimensional, no, we are using this meta surface basically. So here it can meta surface can contain, for example, yeah, a simple meta surface will contain, yeah, reflector or without reflector. You will have a, yeah, array of elements, right? So this meta surfaces, right? You can use for multiple applications. Like for example, it can be used as a radar absorber, radar, RAM used as a radar absorber material, like that. Radar absorber material. It can be acting as an FSS also. So depending upon the, see, the design, what you are doing, see how we are going to meta surface. No, I think last week I shared one paper to you, right? I think
Mm.
meta surface basics of meta surface and all. So whenever a signal getting impinge on that, so how you are going to divert? Either you pass it, you pass it, or you divert like this, or you reflect it. So the design will decide, dictate me that okay, how my meta surface is going to function. See, it's basically in layman language, it's an array of unit cell elements. That's it. Okay, array of unit cell elements. The way you design the what it indicates is that, see, the phase gradients, for example, phase distribution among these things. So phase gradients, right? How we are going to achieve these phase gradients? So the series of phase gradients that will dictate you that okay, the either reflection or diffraction or a negative diffraction or absorption, all will be dictated by that one. So for example, let me say, you might have seen so many papers like a square patch can act as a has been used as a absorber, sorry, not absorber, it can be acting as a reflector surface, reflector unit cell element, or it was been acting as a the FSS also, right? So in FSS part, what we will do, we will remove the ground plane and then we will use it as a FSS, right? So that configuration, the configuration of the element or a configuration of these meta surface will dictate you that will dictate you that how uh, how you are um, uh, whether you're going to achieve the reflection or the absorption or diffraction or manipulating the waves or cloaking structure. It can be a cloaking structure also. There is one another concept called cloaking, optical cloaking, electromagnetic cloaking. Many concepts are there. So the only thing is how the how I see by using the configuration of this geometrical configuration of the structure and the meta surface. So, what phase gradient you are achieving? So the that, and I think Ni in that the paper, Ni sin theta I and Nr sin theta R, like that it might be mentioned, right? Ni sin theta I means incident wave characteristics. Nr sin theta R means reflector wave characteristics. So here, no, the phase gradient will be there. The one parameter called phase gradient. I actually just forgot that formula. There is a phase gradient value will be there. Okay. So and the unit cell size will be there. The spacing between them, dou phi by dou x. So phase gradient in in this spacing, what phase gradient you are achieving?
What?
Accordingly, this incident wave and reflector wave can be modified.
What is phase gradient, sir?
Phase gradient means, see, the only thing is the phase distribution, we can say. The phase difference between these two units, basically. Okay. So the gradient means what? The difference between these two, correct? In
Yeah.
terms of spacing. Yeah, that's what we are saying.
Okay.
And this particular location, in this spacing, what is the phase difference between them? So that will dictate you that either reflection or, FSS or whatever it may be. Yes. Initially, I was also confused. So, what is metasurface? What is FSS? So many terms are being coined now. For example, artificial magnetic surface. So, so many artificial magnetic surface is also same thing. For example, you can use same simple square patch to make it, but the concept is, the way the configuration is different. For example, artificial magnetic surface, what we will do, we will have, for example, why we use this is a substrate. You will have a ground plane, okay. Then you will have a patch, okay. So what happens is, as I mentioned, so in the patch principle is, for example, plus two, positive, 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 negative, negative, like that. Okay. So if you are supplying like this, here it will be in this side, it will be negative, negative, negative. Here it will be positive. In that case, it will be positive. Kind of, I think the current will be flowing from the energy state to this way. This way, I think this way it will be flowing. Okay. So what happens is, see, here no, the what happens is, see, some surface current in the bottom, right? So this will see, so some reflection is happening. See, the radiation of the patch antenna is contributed by this the fringing field, and some waves are getting reflected and coming back, right? These the waves that are radiated, direct radiated wave signals, and also the one the due to the ground plane, because it is a finite ground plane, it's not infinite ground plane, where you will see some diffraction here, right? Because the wave that is propagating here, it will have a diffraction like this, right? Okay. So this can cause the constructive and destructive effect, right? So when can you avoid that? See, for example, some waves are coming over here and going back. Okay. So you need to have a 90-degree lambda by 4. The substrate size should be lambda by 4. Why we are calling it as lambda by 4? For example, this is the patch, this is the ground plane, let's say. Okay. This is the ground plane. Between these two, there is a substrate of lambda by 4. If it is lambda by 4, for example, the wave will travel like this. Lambda by 4 means 90-degree. So ground plane will create this plane reflector. You should not call it as a ground plane. It's a plane reflector, or we can say that plane reflector. We introduce a 90-degree phase shift. Again, it will come back. Again, 90-degree. So total is 360-degree. Total is 90-degree coming back, coming here, and then a 180-degree phase shift. Again, it is going back by 90 degrees. So the net phase effect is, here it is 0. So the waves that are contributed by ground plane also will be in phase with the wave that has traveled, that is that is propagating from the patch, right? That is generated by the patch, or we can say EM that is generated by the patch. Okay. So, but lambda by 4 size, substrate thickness of lambda by 4, imagine that. So that will have how much loss it will have. Leave alone loss, how much cost it will be. Practically, it is impossible to have a lambda by 4. Let's say, for example, for 10 gig, you will have lambda by 4 is 7.5 mm. 7.5 mm thickness is, huge. How are you going to handle that substrate? It will be huge, right? And that's why we don't go for that. That's why we were compromising the performance of the patch antenna, right? In order to bring back that, compromised performance. So what we can do is we can use AMCs, right? What we can do is we can have a AMCs. Okay, we can have a AMCs. Okay, what it does is, see, artificial magnetic conductor means, see, perfect electric conductor is, it will reflect with the 0, means 180-degree phase shift, right? At the same time, magnetic conductor, it will be 0 phase, basically. The perfect magnetic conductor, it will be introducing very 0 phase, basically. But perfect electric conductor is almost possible. Perfect magnetic conductor is almost not possible at all. That's why we are calling it as artificial magnetic conductor, AMC. So what it does is, see, you are, going to see IMC will contain, for example, let's say, you will have a patch array of patches, okay, like this, unit cells. So we can call it as unit cells. Then you will have a substrate. Then you will have a ground plane. This is the master substrate basically. So here you are printing with some antennas, for example, X, Y, Z. Okay, it can be cross dipole or anything. Okay, but this master. I mean, this is the antenna substrate. But the bottom one is configuration is the AMC. Instead of reflector, what are you going to do is you are going to use AMCs. So you can use a thin substrate for this application. But at the same time, what will happen is, see, whatever phase is coming, it may be lambda by 8 or lambda by 10 size will be there. So this phase is negligible. So the wave that is traveling towards this AMC, the phase introduced by this is negligible. So it will reflected with the zero phase. So therefore, you will not get much destructive effect basically. Thereby, you can enhance the gain of the antenna. So what it does is, see, instead of backward wave, for example, if you have a substrate like this, a patch, then the ground plane. So you will have a backward radiation because the current is flowing in this reflector basically. So that will, and also you have the edge that is diffracting, due to which you will have a side lobes, back lobes, many things will be there. That you can subtract, you can have so the what you are doing, whatever it getting reflected, so when a wave coming impinge on this getting reflected, so there will be some kind of flowing, the reverse current is flowing in this one, right? So that wave, no, it will not be there. If it is a 0 degree, it is coming back. So you will avoid these back lobes. Those power getting concentrated in the main lobe itself. So what we are doing? So because in the radiation pattern, no, radiation pattern means what? It is a the spatial plot of, for example, a power distribution basically. At this degree, what is the power level? At this degree, what is the power level? At this degree, what is the power level? So it is we can consider it as a point source, placed on the origin of the sphere. Okay, so whatever in each direction, how much it is radiates in terms of power value. That is what we are calculating as an angle of as a function of angle. Then you are plotting it as a radiation pattern, right? So here what it does is, so backward radiation being, because due to the reflection, no, the destructive effect, we are avoiding that. It is reflecting with a zero phase, which is almost in phase. So what happens is, whatever is coming back, it is getting added in the main lobes. Okay. So that is why, your main lobe enhances. For example, your patch antenna main lobe, no, will be something like this. It will be broad, but low gain. Okay. But here it will be, because, the backward radiation is getting constructively added. Therefore, your gain is getting increased. So the beam is getting focused, which is the directivity. That is why we call it as directivity, right? Directivity means what? How directional is your beam? So how much power can be focused in a particular direction? So it will be focus will be more, right? Therefore, the gain is getting enhanced. This is one of the application of AMC. Okay, and you can also use this for biomedical applications, where you can see that the backward radiation should be nullified, so that because the device that is fitted on your body should not they should not have radiation in the backside, right? Should not have any back lobes, because it will affect your skin, right? That point of time, you can use either EBG or AMC. What it does is, it will avoid, reduce the back lobes, basically. Okay, it will only, monitor your body health in terms of through some way, because there's some mechanism, and then it will send the signal. It will not have a huge radiation in the backward side, so that, it can be avoided.
Yeah. So how this is related to observer or reflector?
Oh, 1 minute, please. Harshini, please close the door. Please close the door. Yeah, sorry. Sorry, please. Yeah, please. Please go ahead.
Yeah.
Yeah,
So
please go ahead.
yeah, so I was asking, so this is the fundamental principle of observer and reflector.
Yeah, exactly. See, the thing is, let's say, let us take, fundamental absorber means, see, what it does is, there is a, the exactly opposite of the reflector, basically, reflection, basically. Okay. So reflection means, see, either reflection or, transmittance. See, let's say this is the reflector ray. Okay. Okay.
Mm.
So a wave getting, in layman language, wave getting impinged on that, it excites the current over here, right, in the patch, correct?
Yeah.
It will, unequally, it will be excited in all the elements. But this current now will produce the field, right? That's how we call it as, reflection, right? Okay.
Yeah.
This will produce the field and get a reflector. Okay. So if you apply some phase distribution on this, so then indirectly what you are doing is, see, I mentioned this before also. So you have a patch. Okay. Again, coming back to the same thing. So you see, the effective dielectric constant is a function of the patch size, right?
Yeah.
Correct?
Right.
Correct? So the effective dielectric constant getting changed. So when the effective dielectric constant getting changed, what will happen to frequency? Get changed, right? Because you are saying that lambda g, correct? So
Yeah.
when a medium, when a wave impinge on this substrate, so the wave propagating within the substrate, it will become lambda g, not the no more lambda naught, because okay, lambda g is a function of lambda naught
Yeah.
divided by square root of epsilon r. Sorry, square root of epsilon r. Okay, so when the epsilon r is getting changed, lambda g is getting changed.
Yeah.
Lambda g is getting changed means it will be always less than the lambda naught, right?
Mm.
So, for example, see, you are having a lambda naught like this, okay? But a lambda g is going to be
Reduced. Yeah.
something reduced, right? So, what will happen is, see, if you take this as a reference point, okay, or if you take this as a reference point, sorry, this is a reference point, okay, what is the phase here? It is more than 90 degree, whereas here it is simply 90 degree, correct?
Yeah. Yeah.
Correct?
Yeah.
That way, that way, see, when you have a non-uniform or uniform elements with the different configurations. So what you are doing ultimately, you are changing the effective dielectric constant of the array elements, right?
Yeah.
Therefore, so when a wave impinge on that, the what is happening? Your lambda g is getting changed. Lambda g getting changed means indirectly what is happening? There is a change in the amplitude and phase, correct?
Yeah.
Of the signal, correct?
Right.
That's what dictate you that the how you are manipulating that amplitude and phase, so that reflected signal will collimation, right? The reflected signal will be the effect of the whole structure, right? So
Mm.
we accordingly getting changed. That's it.
Okay.
Correct. So for example, see, array theory you might have studied, right? If you see this signal, no, this signal will be, you can calculate this offset, right? This offset, correct? Okay.
Yeah.
So yeah, see for example, if you take this as observation point, this is far closer, but this is far away, right? Correct. Okay. So what you have to do is you have to introduce a delay over here, or we can call it as phase. Delay or phase is same. Almost, it's a complement to each other. Delay we call it in terms of frequency domain. Phase we will call it in terms of time. Sorry, time domain. Delay is in terms of time domain.
Yeah.
Phase will be in the frequency domain, right? Okay. So what is happening? You have to delay this signal because now it has to reach right this point.
Yeah.
It has to reach this point. Till that point, how much delay you have to give? This is the offset, right? Calculation of offset, correct? So
Mm.
how much you are having the offset? For example, your distance between these two is d. So what will be the cos theta? So if you want to calculate this one, you have to calculate cos theta, right? Cos theta. This is the theta. Cos theta means adjacent side divided by the hypotenuse, right? Correct?
Yeah.
Let me draw it here. Okay. So this is the observation point. This is the observation point. Okay. So how much is the gap? Like this. Okay. So this is d. This is hypotenuse, correct? This is theta. So cos theta will be adjacent side. Let's call it as a x.
So just a second.
X divided.
Just a second, please. Just a second. 1 second, please. Okay. Yeah. Please go ahead. Yeah.
Yeah, x divided by d. Correct? Cos theta will be. If you want to calculate x, it will be d cos theta. Correct? Okay.
Yeah.
So that much offset you have to give, correct? In terms of phase, correct? Okay. So how much you can calculate offset? It is very simple. D cos theta, correct? The offset is electrically it is D cos theta, correct? Distance. You simply multiply by K or propagation constant beta D cos theta, correct? Beta is what? 2 pi by lambda, correct?
Yeah. Yeah, right.
2 pi by lambda. So let us say D cos theta is in terms of lambda, for example, lambda by 10, something like that. Okay. So 2 pi by lambda into lambda by 10.
Yeah.
The lambda get cancelled. This will be 5. Pi by 5, which is 60 degree. Correct? Correct?
Yeah.
So that is the phase you have to give here. So that, see here it will be 0. Let's say it's a relative phase only, right? Net phase is 0, so that it can reach early. It can be, for example, 30 degree or 40 degree, for example. It can reach next. Then it can be further 30 degree or 40 degree, can reach next. Correct? That's what we are doing, right?
Yeah.
Okay. This is for the reflection. But if you want to, make it as an absorber. So absorber, again, I'm taking this concept only. So I have mentioned that multiple times that, see, what is LXC, which is 1 divided by J omega C, correct? A capacitance by angular frequency, correct? Angular frequency. So the angular frequency is 2 pi F, correct?
Yeah.
F naught. But it is F naught. It cannot be F naught, right? When a wave propagating in the medium, angular frequency cannot be F naught, right? No more F naught. It will be F is equal to C, lambda G. Okay. Okay. It cannot be C also. It can be nu lambda G, right? Nu can be, it will be C divided by square root of epsilon r mu r, right? Because C is nothing but your epsilon naught, I think square root 1 by square root of epsilon naught and mu naught, right?
Right.
Correct?
Yeah.
Right. So see, when you propagate, for example, see, this is the wave. When it propagation within the medium, it is no more C, simply C, free space velocity. It is going to be as a function of epsilon r mu r, correct? Okay.
Yeah.
Correct? Correct. So when you modify this, what you are doing indirectly? You are modifying the velocity.
Yeah.
That's why the phase velocity come into picture. Right? There is a phase velocity come into picture. Okay.
Yeah.
So I wanted to show you that as well. So how phase velocity means phase velocity come into picture, right? Okay.
Yeah.
Phase velocity is, so these velocities will change, right? Whenever it impinge on this signal. So velocity is getting changed in terms of phase also. So phase velocity means, see, so many waves are coming impinged under reflector back. So a wave is like this, another wave is like this, another wave is like this. The relative phase, okay, how the phase is getting varied among the waves, that is called as phase velocity. Okay.
Yeah.
And another one is group velocity. Group velocity means, as I mentioned before, right? For example, your wave is moving. If it is all the waves are having same phase velocity, and then what happens is you will not identify any changes, right, between the waves, right?
Right.
Correct. For example, as I mentioned in a simple example, right? When two buses are going, you and your friend is sitting in both the buses, So when both the buses are going in the same speed, 200 kilometer, 100 kilometer speed, you will not see the difference, right? Correct. You will see that as if you are sitting in some hall, correct? You will feel that ideally, if there is no vibration or something like that. But when you're having, to and fro, for example, one bus is running in 120 degree, 120 kilometer per hour, the other bus is running in 100 kilometer per hour, then you will see the difference, right? Bus is crossing. Okay. So the net group velocity is varying, correct? But when you have both the buses are going in the same time, which means group velocity is nothing. It's same. Okay. When you have a group velocity is 0, but when you are having, the difference between them, the group velocity exists. Correct. So all are, the wave, phase velocity, all concept will come over here, correct? So the coming back to this. So as I mentioned that the phase velocity is going to change. Okay. Indirectly, what you are changing? Phase frequency changing. Frequency changing means wavelength is changing or
Well,
angular frequency changing. Indirectly, what you are changing? Reactance is getting changed, correct?
hmm.
Okay. So it's similar, the whole it hold good for XL also, right? Inductance, reactive inductance, right?
Yeah.
So L and C you are modifying. As you know that, see, L and C, LC can form a tank circuit, correct? Okay. So
Yeah.
this L and C, if you manipulate these two, it can be acting as a, absorber, correct? This
Yeah.
is L and C, basically it's a storage device, right?
Yeah.
Okay. If you currently write this into L and C circuit, currently what you are doing, see, L and C, you can configure for anything, right? For example, it can be it can be for storing device, or it can be for the capacitor. You can, it's a storage device. So it can be for a storage device, or it can reflect. So many things you can model, right? So when a wave impinge on this, so depending upon this, the structure, the effective dielectric constant getting changed. So effective dielectric constant changing means what is happening? There is a change in the velocity.